Well, welcome to Class 5, our last class before the break. We have a one-week break after this, which is a good chance to catch up. Charles, I have a question that actually I wish I'd thought of to ask you, but was asked a couple of weeks ago, which is in the forums. The question, which was, I thought, particularly insightful, in the stuff we've been discussing so far, we've clearly been discussing wavelengths of light, red, whatever. Of course, anyone from a physics background will tell you that light has a duality in its physics teaching.
Yes.
That of being a wave, but also that of being a particle.
Right.
And I think the question, and I'm going to paraphrase now, comes down to, are there any instances, especially with sensors that are, of course, very, very dense and very high resolution, like 4K, whatever, where the particle nature of light actually comes into play?
So this is a great question. And absolutely right, during the color portion of the classes, we've been talking about the waves and the wavelengths. The wavelengths are directly related to energy levels of each individual photon.
Yep.
And the mathematics is reasonably simple. It's the wavelength divided into the speed of light gives you the energy. And it is that energy.
And of course, speed of light being a constant.
And speed of light is a constant. And it is that energy that when the photon impacts the silicon of the semiconductor sensor, lets loose an electron. So that energy does have a lot to do with how the sensor works.
So you're saying at the actual sensor level, what the sensor is doing is basically being an energy reader?
Well, that's a very tricky question. You might think...
It's a 300 level course, and you're
Charles.
Charles.
Well, now, but we're headed to 4. So.
Okay, good. I'm there.
So over the scale of visible light, one photon has got just enough energy to let loose one electron. If you're dealing with shorter wave, higher energy photons, like ultraviolet photons, you might let loose 2 electrons because of that excess energy.
Okay, but that would make sense, right? Because there's a continuum from visible light up and down the spectrum to much more obvious electrical...
Well, there's a continuum on the energy levels of the photon, but you either knock loose 1 or 2 electrons, nothing in between.
Okay, so now we're into quantum considerations.
Absolutely we are. So when it comes down to collecting those electrons, what the sensor does, and I'll draw the sensor as if it's vertical and the light is coming in here. So in the depth of that silicon, the sensor is collecting those electrons. And now, directly relevant to the question in the forum, that number of electrons collected is an integer.
Okay.
Because electrons only come one by one.
Yep, absolutely.
So you'd like to collect as many electrons as you can. You'd like, ideally, to have a deep, we call it a well, although the electrons go into the well, it doesn't come out.
Sure.
But we talk about the well collecting those electrons. And
because if I didn't have a deep well, I'd have a sampling problem.
Well, it's more than the sampling problem. The sampling problem certainly does come into this. But more than that, you just want to collect as many as you can. You want to collect as much light as you can. And so basically, the larger the pixel is, the better from that point of view. But the larger the pixel is, the worse your spatial resolution is. Yep. So there's a very interesting trade-off.
So that begs the question, how far are we towards these becoming real considerations? In other words, are we, because for example, if we're talking about semiconductors,
yes,
you get to a point with a modern day semiconductor where people start saying, okay, well now we're starting to seriously get into the atomic design of these transistors. They're so small that some of these materials we're dealing with are absolutely affecting how much more efficient we can be. So at the chip level, are our wells so big that the size of a current sensor really isn't a consideration at all? Or are we getting to a point that actually I really have to pay attention to make sure I have got enough photons hitting that, especially on a high-speed camera like a Phantom or something?
Indeed. Well, you do have to absolutely pay attention today. The problem is of the well capacity is worse as the pixels get smaller. So that particular problem is now affecting cell phone class or iPhone class cameras because they want to make very, very small pixels. They want to achieve 5 megapixels of sensor in a very, very small size. So for them, the small pixels are a big constraint. In our world, either HD with a 2/3 inch diagonal on the sensor, it's not such a problem, and in a cinema class sensor, not a serious problem. But it absolutely does affect the noise performance, how many electrons you can collect. And the more you can collect, the better.
Okay, I'm going to follow up with that later, but we'll get to the class because I've already distracted you enough. Let's check out this week's class.
Good. I'd like to pick up on an important color science topic, just as a little addendum to the previous talk on color science. This is a representation of a standard color blindness screening test called the Ishihara test. And most of you will be able to look at this disk of what amounts to colored pebbles and see in it a number. Now, whether or not you can see that number is a function of how the spectral properties of those inks relate to the spectral properties of your vision. And I thought this would be an interesting example to show, first of all, because I want to reinforce that a camera will pick up colors properly only if its sensitivities are a fairly good match to the sensitivities of human vision. And the Ishihara test is designed to tease out properties of human vision, so we should be able to use it to tease out properties of the camera. Now, I'm assuming that when you're looking at this as imaged and recorded through the camera, you are distinguishing those colors in the Ishihara plate. In other words, we hope that the camera is not colorblind. But more than that, we hope that the camera is reproducing colors reasonably close to those that would be perceived by a normal human observer. So I haven't gone to the depths of working out exactly how to make sure a camera mimics the color performance of vision, but this might be a good start. Now, in Class 1 and Class 2, we had a long discussion about what particular set of 3 curves you should use in a camera to reproduce color correctly. And we started that discussion with the long wave, medium wave, short wave curves, or the LMS curves, which reasonably closely mimic the physiological properties of the human visual system. But we also discovered that it's useful computationally to map the LMS system into the XYZ system because the Y channel mimics the lightness sensation of vision, and that's very useful for image processing and color processing terms. Now, I do want to add one little piece to that story, which is in certain very special conditions, there are applications where the color matching curves of the CIE standard are not the right ones to use. And the example is quite relevant to digital cinema imaging because we're used to digitizing film. So think for a moment about digitizing color film. The problem there is not so much digitizing color as it's perceived. You can imagine if you're digitizing color negative film, the color isn't even sensible as it's developed on the film. I mean, when you look at a piece of developed camera negative film, there's colors, but the colors that you see somehow encode properties of the scene, but it doesn't look like reasonable, sensible color at all. When you're scanning color negative film, or even when you're scanning print film, I wouldn't recommend that you do that, but some people do and some people have to. Print film colors are at least supposed to be sensible, but your task is not analyzing spectra per se. Your task is really extracting the 3 amounts of dye concentrations that were formed from the scene. You're one large step removed from the scene. And when your goal is just extracting the dye amounts, you might be better, in fact, you're usually better, using curves that look like this. Now, I wouldn't recommend using curves like this to sense an original scene, but these curves are designed to just extract dye concentrations pretty much at 3 individual wavelengths. Those curves are appropriate for a scanner, but not for a camera. In the previous class, we had a long discussion about quantization from 0, take it as black, to some maximum number, whether that's 255 or 4096, whether it's 8 bits or 12 bits, is up for discussion. And we talked about quantizing linear light values, and that's exactly analogous to the Academy Scene Linear Scene Referred Image Interchange Framework. I'd like to talk a little further now about quantization, and in particular I want to talk about what we do in practice to reduce the bit width from something like 12 bits or even 14 bits appropriate for linear light acquisition to something like 10 bits or 8 bits appropriate for distribution purposes in a perceptually optimized space. So the concept behind quantization is to take a continuous set of values, and here I'll map them just from 0 to 1, but in effect 12-bit linear light or 14-bit linear light can be considered to be, in practical terms, continuous. And quantization takes that continuous set of values and maps it into a discrete number of integers, usually drawn in a straight line. But here, when you map to an 8-bit quantity, as I indicated in the last class, we usually do so through a nonlinear mapping optimized for perception. Now, I want to give you a kind of deep conceptual grounding behind that perceptual business. And to do so, well, first of all, it's the Chinese fortune cookie, fortune. 2 small jumps are sometimes better than 1 big leap. This was actually a fortune cookie I got at dinner one night. So the idea is taking 2 small steps might avoid banding, where taking 1 giant leap might cause a visible jump between those levels. Now, in principle, there's lots of places where we'd like to be linear, and linearity simply means a set of mathematical operations that obeys each of these 2 laws. And I won't even bother reading these to you, but this is a mathematical definition of linearity. However, none of the mathematics says whether you're linear in the domain of physics or linear in some other domain. In other words, you could apply these equations to a physically linear situation like counting photons or measuring optical power, but you could also apply these equations to values that have been obtained from light values from a scene, but mapped through some nonlinear curve. Now, that's exactly the case with video. We take linear light values in front of the camera and map them through a curve, casually called gamma correction, to get video signal numbers. We usually deal with them between 0 and 1, or if you wish, 0 and 100 units or 100 IRE units. But it's easier just to think of them 0 to 1. But those numbers do not go in proportion to the light values in the scene. In the linear light domain, an 18% reflector in the scene, a Kodak gray card, say, reports the number 0.18. But once mapped through an HD camera, an 18% reflector in the scene reports a number usually something pretty close to halfway up the scale. So it's really not useful to call that mapped quantity linear, even because linear really in our business today should be reserved for linear light. Now, I should warn you, as I think I warned you at the end of last class, that there are a lot of digital imaging technicians who very loosely use the word linear, but really they're talking about video coding, where they think that these equations hold, but the quantities that they're talking about are perceptually mapped quantities. So be very cautious when you hear the word linear. Remember to yourself, linear is just an adjective. And when you hear the word on its own, you better go and explore what the noun is that it's modifying, whether that's light power or video signal. Now, to give you a very broad, loose concept behind why this matters perceptually, I show you a bunch of shapes of the letter A where the size of the letter proceeds by a physically linear 2-point increment every time, and another group of the shapes of the letter A where the letters increase in what you could call a geometric progression. The type size of each of these letters is 1.15 times the previous one. Now, the thought experiment is, which of these sequences seems to be progressing at a uniform rate? And I think you'd agree with me that you can't really tell the difference between those two letters, even though one of them is 2 points larger than the other. And this progression does not seem to be uniform. However, this is the physically linear progression in terms of type size. This progression seems to be uniform, but actually it's proceeding by ratios. And I give you this as a conceptual example behind nonlinear coding. This set of letters, because it proceeds by the ratio 1.15, is conceptually equivalent to the light levels that you'd like to code into the imaging system, although light levels you'd better use a ratio like 1.01 instead of 1.05. But it's still this geometric progression. Now, just to hammer this point home even more, I'm going to give you another example. This is what a potentiometer looks like. It's an electronic component. You feed a signal in one end relative to a reference at the other, and where you position this lever determines what fraction of the signal you pick off. This could be the volume control on a radio. Now, more likely, your old-time volume control was actually rotary, but it's exactly the same electronic properties. There's an input, a reference voltage, and an output tap that's some fraction along the rotation. Now, the simple, easy, straightforward way to build a volume control is build it to tap a linear amount of signal across that rotation. But if you do so, something really interesting happens. All the action ends up at the bottom of the control. And the action ends up at the bottom because our hearing system is roughly logarithmic, just like our visual system is roughly logarithmic. And if you use a strictly physically linear volume control, it doesn't work properly. Now, volume controls in early radios, the engineers figured this out in the 30s and the 40s. So they developed a volume control which wasn't linear. It had a nonlinear relationship between the angle of rotation and the amount of signal voltage tapped off. And here I'm giving you the graph directly pulled from a Born's potentiometer catalog. These are the guys that actually make those physical components that are the volume controls. And the standard audio taper, as they call it, is in graph 2. Well, there's a bunch of different tapers you can get from these controls, but the volume control version of it is -2, and going halfway up the rotation of the control only gives you about 10% of the audio voltage, but that sounds halfway between nothing and full volume because of the logarithmic properties of vision. And now, directly related to this, I'm going to give you an excerpt from the release notes for Apple iTunes 4.5. Because it's going to be difficult for you to read, I'll read it to you. The volume slider in iTunes 4.5 is now logarithmic, like most stereo volume knobs. This makes it have a more useful range, but you might, well, don't worry about that part. Human hearing is logarithmic, which is why stereos have log volume. We got complaints that iTunes didn't have log volume, which meant that when you adjusted the slider, you could move it a lot at one end, and it doesn't sound much different, one end being the top end, while at the other end, the bottom, moving it a little made a big difference. Well, they fixed that. So with log volume, moving the slider an equal amount changes the volume by the same amount, should really say the same perceptual increment, throughout the entire range of the slider. Now, just to keep the real iPod enthusiasts happy, they end with this little note: the maximum volume did not change. We didn't reduce the volume for you. We just changed how it's mapped along the curve. Now, what Apple are basically saying here is we finally made iTunes work the way human hearing expects. And the shocking part of this whole release note is the fact that this is not iTunes 1.01. Like, why did it take them 3.5 years to figure this out? But the point is, audio is coded according to perceptual principles. We build the perceptual principles into the engineering of the system. Now, for imagery, to code it into perceptual space, which is the most efficient space, we do that too. And so we build into the engineering of an HD camera the gamma correction curve. I'm putting quotes around it because the term gamma is highly ambiguous. But we'll go into the details of it later. The key point, we build into the engineering of an HD camera a consideration relating to how humans see light levels. And it's very much like the inverse of that volume control curve. It's a curve that looks like this. And at the other end of the system, we more or less invert that curve so that end to end, it's pretty much linear reproduction of the photon count, pretty much. But in the middle, to make it perceptually efficient, it's not coded linearly according to light power. I'm showing you a piano here because the distribution of frequencies, which in the case of a piano are logarithmically arranged, or more accurately, you should say exponentially arranged, so that the frequency of every key is 2 to the power something, where the exponent changes by a fixed amount. Now, some of you might have heard of the 12th root of 2. That's the ratio of the frequencies of successive keys. Well, successive semitones, because the keys really go this one, this one. That's an exponential sequence of frequencies. And of course, people 2,000 years ago in Greece figured out that, sorry about that little warp at the beginning of the note, but this frequency and this frequency are related by a power of 2. Well, this frequency is simply double this frequency. Now, our hearing hears tones in that logarithmic manner, and that's how that's how Western music came to have the notes that it has. This is the graphic that I used to show light levels over a ratio of 1,000 to 1. That is 10 stops, 10 photographic stops, or alternatively, 3 density units, where a density unit is a factor of 10, a stop is a factor of 2. Now, in principle, in theory, you would think a stop should be exactly a power of 2. But there's a very interesting numerical coincidence that 2 to the power 10 is very close to 10 to the power 3. 2 to the 10th is 1024. 10 to the third is, of course, 1,000. Because those numbers 1,000 and 1,024 are so close, for scientific purposes, it's convenient to divide that ratio of 1,000 in light level into exactly 10 stops. So for science purposes, it's useful to take a stop as being 10 to the power 0.3, which turns out to be about 1.995. But let's call that a science stop. That relationship says that there's exactly 3 1/3 stops per density unit. The photographers, the cinematographers, even the colorists like the stops. The scientists like the density unit. It's very convenient to form a numerical system where those two mesh. And that's achieved by taking a stop to be a little tiny bit less than a factor of 2. So in photography, it's very rare to find anyone talking about a half a stop. Everybody talks about 1/3 of a stop because that's the magic ratio that folds into the power of 10 density units that are used by the photographic chemists and scientists. And now in the modern world, we use log coding in cameras, and we're taking advantage of the fact that perception operates roughly logarithmically. So back to the keyboard, from this note to this note is an octave, and we divide that into 12 equally spaced semitones. But that relationship doesn't sound very good. What sounds better is a progression that goes, which is, of course, the do, re, mi, fa, sol, la, ti, do. And it's a very complex relationship between those frequencies. What's important for our purposes is the piano mimics logarithmic coding. Each decade, each power of 2 has got the same distance. Each power of 10 has got the same distance. So to me, it forms a good mnemonic for the logarithmic coding we use in log coding of camera data signals. Now, let's get technical about what's exactly in the camera, either a cinema class camera or an HD camera, and have a discussion about what those curves need to be or should be. So to start, we use the special word luminance, and luminance, as you'll remember from class 3, I think, is a weighting curve on the spectrum from 400 to 700 nanometers of a very particular shape. It's not a mathematical shape. It's not a raised cosine or a Gaussian or anything like that. Instead, it's a curve joining a set of numbers established by statistical experiments with human observers. So the curve is numerically defined, and then we just interpolate in between the points. It peaks at 555 nanometers and vanishes in the ultraviolet below 400 nanometers, vanishes in the infrared above 700 nanometers. Now, your camera should have optical sensor circuits that allow you to mimic something reasonably close to that curve. Now, I've plotted a second curve here, which is the sensitivity of the rod cells in the retina. So let me backtrack a little bit. That entire discussion we had about color vision in classes 1 and 2 were about the 3 types of cone receptor cells on the retina. But I didn't at that point want to introduce the 4th type of cell, which, if you look at them in a microscope, have the shape of a rod. The rod cells are completely optimized for vision at extremely low light levels. So low that normally in modern Western society we don't ever even need the rod cells. You could call them night vision. And for purposes of color image reproduction, well, they're not useful because there's only one kind of them. In order for humans to see color, we've got to have enough light to cause the cone cells to function. And in color vision, the rod cells are not useful. Now, I mention that because there is a lot of incorrect information floating around about how the cone cells are for color and the rod cells are for black and white, or the rod cells are for luminance. That's not correct. The rod cells are for extremely low light levels, so low that you're not using color vision. Now, that curve is the luminance curve, and we'll be speaking in the next 5 or 10 minutes about how cameras map luminance. You saw this experiment, I think in class 3, saying basically that whenever the ratio between two luminances falls below 1.01, roughly speaking, nobody can see the difference. And that logarithmic relationship, that 1.01 ratio, implies that if you were simply to code luminances according to the logarithm, you would be able to code integer values that are just one just noticeable or one just unnoticeable difference apart as you march up the scale from black to white. Now, we could do some arithmetic that says how many codes would you need to cover a reasonable contrast ratio, and that arithmetic works something like this. You need something like 462 codes to cover a 100-to-1 contrast ratio. But that's really a theoretical number. It turns out in practice that that ratio gets less demanding as you drop down the luminance scale. So at a luminance of 1/10 of your adaptation level to the scene, that ratio has increased to maybe 1.05 or maybe even 1.1. And by the time you get to 100th of the adaptation level, the ratio is increased to quite a large number. So the ratio loosens up as you adapt up and down the scale. And there's another experiment that you can do different from this one to try to get at what is that kind of behavior. What kind of luminance levels do we need to code so that we get the minimum number of codes but still satisfy the requirements of human vision. The other experiment you can do to get at that information is this one. You have got two fixed luminance levels kind of at both ends of the scale, not as far away as black and white, but considerably distant. And you have a variable luminance in between under the control of a psych undergrad student who you're paying approximately $5 an hour. So this student is instructed to wing the knob back and forth until the luminance level of the central patch is perceptually halfway between these two bracketing luminance levels. And when you do this experiment, you find that the curve that you pull out of the human visual system is not so much a logarithm, it's more like a power function. And a bunch of different researchers in that community have pulled a bunch of different curves from a bunch of different experimental situations. But roughly speaking, these can be well approximated by power functions. And the curve that was standardized in 1976 by the color science experts, La Commission Internationale de l'Éclairage, so now you know I'm a Canadian guy, I can speak at least 3 words of French. That standard curve is CIE L star, and it's the one that goes ... in the middle, and it's very well approximated by a 0.42 power function. So the proposition is that on the way in from linear light photon counts or optical power measurements in front of the camera, on the way into a compact coding system, L star would be a good way to do it. And then on the way back out to a display, you need to map back out into linear light. And the way to do that would be invert that curve. Well, 1 over 0.42 is 2.4. So the way out should be a 2.4 power function. Now, what do you think is the mathematical equation that describes the behavior of a broadcast video studio reference monitor? 2.4. That's no accident. It's almost exactly the inverse of human lightness sensitivity. So it almost perfectly inverts that perceptually uniform code. That's video code. Now, it turns out that in a camera we don't come in with a 0.42 usually. Usually there's a certain mapping that we'll discuss the remainder of this class and maybe spilling a little bit into the beginning of the next class. A mapping that depends upon the viewing environment, the viewer's adaptation, the absolute luminance. Certain factors fold into it, and we'll discuss all of those. But to the first approximation, the camera does something like a 0.42 function, and it's almost always the case that on the way out to an HD display, that's a 2.4 function. Now, the video guys never properly standardized that function until March 2011. And there's a new standard from the ITU in the same series as recommendation BT 709. The new standard is BT 1886, and it says basically, thou shalt map out to an HD reference display with a 2.4 function. And so keep in mind, that's the function that inverts the perceptual properties of human vision. Now, the standard that we used to think was appropriate was this one. It's the 709 standard. The standard itself doesn't provide this graph, but it provides the equations, and it's trivially easy to draw the graph from the equations. So the equations in 709 say that when you map from linear light value to video code, both on the scale 0 to 1, so somehow we've normalized to a white patch or some absolute luminance value, and the light power is referenced relative to that. And the video scale, I'll just talk about it from 0 to 1. So for the moment, I'm not concerned about extended range and headroom and footroom and 8-bit and 10-bit and all that stuff. Just think 0 to 1. So the 709 standard, BT 709, says do this. Now, you can see immediately that this function has two branches. It's got a linear segment where for very small light power values, less than about 2%, you simply apply a gain of 4.5 to the linear light tristimulus signal. But for 98% of the curve, the upper portion, it's a power function. It's not an exponent. Well, the 0.45 is an exponent, but this is not an exponential function. An exponential function is constant to a power, which varies. A power function is a variable to a constant power. The two are quite different. So this is a power function. It's got an exponent of 0.45. And a lot of people, including, I'm sorry to say, most DITs, will say, oh, yeah, HD camera, gamma 0.45. But you'll notice, if you look a little more closely to the equation, that there's a scaling of about 1.1 and an offset of about minus 0.1. Well, those end up being fairly big numbers, and they have the effect of scaling and offsetting the curve so that its intercept is actually way down here, the intercept of the pure power function, and the linear segment is stitched in near zero so that the function matches and the slopes match. And if you do the math to back this out and say, if I were just to treat that as a pure power function without any scaling and offsetting, what's the best estimate for the power? And the answer to that question is 0.51. Not really that close to 0.45. So roughly speaking, a camera, an HD camera with factory settings out of the box does a mapping that's approximately a square root. But the DITs and the video technicians and the video engineers often call it 0.45, and that's not really conceptually that accurate. Now, if you want accuracy, you just run through exactly this curve. But now we get to a deeper conceptual issue, which is that this is the standard that the video guys have been using since 1990, but they really missed the big point. The big point is what matters in making a show is the mapping from the data that you end up with at the end of the day and the display that you're looking at it on. In other words, anything you want to do up front in production is fair game as long as it delivers the picture you want. To get repeatable results and faithful portrayal, you want to standardize the back end of the system, not the front end. So this curve is useful for engineering purposes, but it's not necessarily useful at all for program production or creation. And in practice, the curve that a real production will use in an HD camera is a curve like this, which I've drawn for myself as an interpolation of the knobs that are available on a typical high-end HD camera, whether it's a Sony, a Panasonic, a Grass Valley, any of the historical HD cameras have got a big gamma knob labeled with numbers from, say, 0.4 to 0.5, actually even more typically from 0.35 to 0.5. And a black gamma range knob and a black gamma level knob and a knee point knob and a knee slope knob and an iris control, which controls overall exposure, and maybe a pedestal control, and maybe blue and red gains in addition to overall camera gains. So there's about 8 or 10 knobs, which in an HD production are completely fair game for the cinematographer or videographer to wing to achieve the effect that they want. So anything they want to do up at the front end is fair game as long as it delivers the appropriate picture. And the goal of faithful display is achieved by a standard mapping from the video signal out to the display. And the recent BT 1886 standard says 2.4 power. Now, I have 2 more quick things to say, and then we'll wrap this class. 2 more important quick things to say. Some of you digital cinema enthusiasts and perhaps red camera enthusiasts are looking at this graph saying, oh, what a bunch of crap that is. The camera should just have a fixed curve and shouldn't have any knobs. We just want to capture the sensor data and do the rest in post, or DI. And that's an absolutely legitimate point of view for cinema or for any production where you've got lots of time in post and you've got creative control and exercise of creative intent in post. But keep in mind for HD, that wasn't always the case. And it's the historical method of capturing video, including HD, to put onto the recording medium data which has been mapped through a reasonable mapping. Maybe the finished color is coded into that data, maybe it's intermediate data, But in any event, the assumption in HD is that you're recording data which is meaningfully displayed through a studio reference display without a big complicated transform. And in the case of shooting RAW, whether that's a RED camera, an RE camera, or even a Sony camera set to S-Log mode, you're not able to view that material directly on an HD display in a meaningful fashion. So there's two different approaches to shooting. Only the HD approach uses all those knobs. Now, second point, before we wrap, when I've been showing you all of these curves, you've probably been thinking of luminance on the bottom scale. That's the linear light values that are our starting point, counting photons or measuring optical power. And that's, of course, the VFX-friendly domain, because the VFX and CGI guys, they just want to work in linear light. But the little wrinkle here is that I stopped using the term luminance on the x-axis and I started using the term tristimulus value. And I did explain tristimulus value in class 1, but now you're beginning, I think, to get the subtle implication of that. In video, we're never really dealing with luminance on this axis. We're dealing with separate R, G, and B values. They are correctly described as tristimulus values, but it's only mixing those together that yields luminance. In HD and usually in digital cinema, we don't even mix them together, though, because we simply transport RGB all the way through the system separately without always mixing them up to make luminance. Now, in class 8 or 9, we'll spend a little bit of time talking about the quantity in video which goes, unfortunately, mistakenly by the name luminance, which is really properly called luma, but it's got everything to do with this distinction between the 3 channels conveying the information and mapping into one channel conveying grayscale information. So more on that to follow in later classes. That's it for this one.
So I have to say, for me personally, I didn't expect when Charles came to do the class that he'd be playing electric piano.
Mainly because I don't know how to play piano.
Yeah, sure. So, you know, the Billy Joel of colour science here. I actually should have worn the Elton John big shoes and the whole pinball wizard thing. But I guess it is to eliminate problems. And also I think it's very helpful to see those non-linear scales happening in so many other aspects of what we consider to be kind of natural, and especially in the case of music, actually, you know, pleasant levels, because it's that pleasantness that is inherent in octaves that, of course, the Greeks kind of identified, which I think started with the banging of hammers on metals, where they first worked out the octave thing.
Oh, I see. The theory, the mathematics behind this was Pythagoras himself.
Who was such a smart-ass that they actually burnt his whole thing down to the ground, because the thing they decided they hated more than a mathematician was a real smart-ass mathematician.
Well, the rumor is that he was kind of a bit of an arrogant guy, maybe.
Well, turned maths into religion, so he's my kind of guy. But yes, it wasn't a particularly good career move in terms of keeping his order going after. But anyway, enough of that. Break week next week, and we're back in week 6. Thanks so much, Charles.
It's a pleasure.
Okay. I had said we were going to finish, but actually we've got one more thing. It's a gift for break week, which is bizarre but true. You want to discuss not air guitar, but air music.
Oh, yes. Well, there's a famous musical instrument which is an electronic instrument called a theremin, invented by Leo Theremin. And I haven't quite figured out the Russia-Paris connection, but his name has got a French accent on it, but he was working in Russia. And he invented this machine which translated the motion of your hand through electrical capacitance into a tone, into a frequency, and the motion of your other hand into control of volume. And the interesting thing about this, relevant to logarithmic human perception is that both of those quantities are logarithmic. We hear the volume on a logarithmic scale, and we hear the frequency, pitch, on a logarithmic scale.
Okay, and so people can play this seriously, though most people would know that sound from sort of 60s, 70s sci-fi movies, right?
Right. That is what it's
This
associated
is a
with.
pretty uber geeky, this is not, your classic kind of Rolling Stones instrument.
Well, and apparently the instrument is incredibly difficult to perform.
Right.
Because it's hard enough to perform.
Because people are laughing at you?
Well, maybe. It would be a performance, though, wouldn't it, if you were on stage with a theremin?
I'm not really into that kind of stuff, but I understand that people are. Okay, well, that's your gift for those of you that are obsessed with this weird logarithmic stuff. But it is exactly the same property, in all seriousness, that we've been discussing.
That's the key point. It's the logarithmic nature of human perception. And that's exactly what leads to log coding in digital cinema cameras.
Okay, catch you after the break.
Howard, did you solve the install time problem yet?
No, it's a little tricky. I'm going to try having it pick up the library's guide.
What are you doing?
Playing the theremin.
No, I mean, what are you doing with a theremin?
Playing it.